Yes,
Can you
yes.
hear? Okay, great. So yeah, thank you, Gabriel, Suresh, and Yang for this invitation. And as Gabriel said, I'll be talking about some aspects of arithmetic statistics of Hecke eigenforms. And so basically, from the ground up means that I'm going to start with the very basics, which is that I will assume no knowledge of elliptic curves or any sort of modularity. Um, so, so it's not really particularly about one paper per se, but it's I will start with the basics, then I'll discuss very briefly some aspects of work that I did with Taizan Otari and Masaki Okada, which has to do with characterizations of two-dimensional rational conformal field theories. Um, and then eventually I'll build up to a small part of a much larger work in progress with Notsage Ilya, who was a mathematician in Mainz. And this falls into something called some computational aspects of motives in the Langlands program. Okay, so what exactly are elliptic curves? Well, I mean, this is a bit of an overview. We're going to start with what elliptic curves are, and I'll tell you that they have many renditions and they appear in many different contexts. And even aside from mathematics, they have a lot of important uses in modern society, for example, in cryptography. So most of your high secure cybersecurity relies on elliptic curves. And in principle, they're also important mathematically because the Lagrange program actually starts off by understanding what the Galois representations of elliptic curves actually are. So I'm going to start with a very brief introduction, very basic introduction to what elliptic curves actually are. And then I'll tell you something about the theory of complex multiplication. So complex multiplication is something to do with the enlarged endomorphism algebra of an elliptic curve at very special points. And I'll tell you a bit about how elliptic curves arise in string theory, since elliptic curves are some of the simplest target spaces, which are also Calabi-Yau manifolds, and they can be tied to rationality of conformal field theories or black holes in string theory. And then I'll move towards zeta functions and the arithmetic of elliptic curves. And I'll give you a brief overview of the Tanya-Mishima. Oh, there's something cut off here. The Tanya-Shimura wave conjecture, which is the modularity theorem. And I'll go over a brief history of experimental number theory with elliptic curves, and we'll have a small ending towards arithmetic statistics of way to Eigenklasse forms. Okay, so that's roughly the plan for the overview, but I'll keep it very basic for most of the talk. So before we start with elliptic curves, one has to start off with the very basics, which is to do with ellipses. So we need to step back and understand what these are. So ellipses are conic sections, and meaning that if you take a conic section, if you take a conic and you slice it with a skew hyperplane, and depending on how skewed it is, you end up with a figure, which this here looks like an ellipse. So you could think of an ellipse, which is a deformed circle, meaning that if you take a focal point of the ellipse and draw a straight line towards the boundary of the ellipse, then the reflection of this straight point will always pass to the other focal point, regardless of which direction you move in, right? So this is basically what an ellipse is. And why mathematicians started studying this, it actually goes back to physics and astronomy when Kepler started studying the planetary motion. So the first two Keplerian laws are that for planets in the solar system, planetary orbits are elliptical with the sun as a focal point. And the second Keplerian law is that the imaginary line joining the sun and the planet sweeps out equal areas in equal amounts of time. Okay, that's kind of fine. And he actually came with a third law as well, but we don't really need a third law at this point of time. But at this point, it's a very important question to ask, which is how fast or how long does the planet go around the sun? Okay, so you would say, okay, that's very easy. You can just compute the distance that the planet has moved, and you would divide it by the time that the planet has moved for. But then that's okay. But how do you compute the distance the planet has moved along an elliptic orbit, right? So you would think that ellipses are squash circles, and you know that the area of an ellipse generalizes. So just like the area of the circle is pi r squared, the area of an ellipse is basically pi times a times b. But if you try to understand what the circumference of the ellipse is, it doesn't really generalize as 2 pi r. So there's no closed form expression that tells you what the circumference of an ellipse actually is. So if you want to compute the circumference of an ellipse, you basically need to use the arc length formula, meaning that you start off with the equation of the ellipse, and you use the arc length formula to determine the circumference as 4 times integral from on the cycle along the semi-major axis times this particular integral over here. You follow a series of substitutions And then once you set all these different substitutions in, you end up with the equation for the circumference of the ellipse, which is basically given by this particular kind of integral, which is an elliptic integral. And what you see in the denominator over here, you could think of this as the square root of some particular polynomial equation. And in fact, this particular polynomial equation, y squared equals x times x minus 1 times x minus k squared, you could think of this as an example of an elliptic curve, right? So what exactly is an elliptic curve, though? So before we actually start talking about what this means in geometry, we have to take a step back and understand what this means in Diophantine analysis. So what is Diophantine analysis? It is an area of mathematics, and especially number theory and algebra, in which you're concerned with understanding what the solutions, integer solutions or rational solutions to polynomials actually are, right? So you consider a polynomial of this form over here. This basically means that I take a polynomial in n number of variables of some arbitrary degree, such that the coefficients are always valued in z, right? So in Diophantine analysis, you ask the two following questions. Does the polynomial have integer roots or rational roots? So in many cases, you will actually see in Diophantine analysis is that for polynomials, integer roots or integer solutions are the same as rational solutions, meaning that if you know the rational solution, so the integer solutions sort of come out for free, right? And if you know the fact that a Diophantine equation has a rational root, can you determine all the rational roots, or that is, can you determine at least one of the rational roots? And this is sort of simple to do for certain cases. So for example, in high school, you have studied that if the degree of a polynomial is 1, then this is pretty straightforward, because then if there exists at least, so let the polynomial be some polynomial k variables, which is all degree 1, and then you want it, basically you can say that then if there's any 2ai, which is such ai or aj, such that I not equal to j, then as long as the GCD of ai and aj divides L, then you can find an integer solution, right? So this is one of the simplest things that you can do in Diophantine analysis. So other examples, of course, are you can find equations to, for example, of let's say Diophantine equation in 2 variables, and for example, a circle. So if we find a particular rational solution, then you can use sort of rational tangency or rational slopes to determine what the other rational solutions actually are. And since there might be number theory, machine learning people in the audience, the question of whether or not you can determine if a polynomial has integer roots and whether you can determine all the rational roots, that is actually a key tenet of Hilbert's 10th problem. And you can rephrase it in the setting of something computational, in the sense that you can ask if there's a Turing machine which can decide if whether or not a polynomial has integer roots. And actually it was shown by a bunch of people like Matiasevich, Putnam, and others that no, such a Turing machine doesn't exist because the problem is not decidable, right? So the question becomes, in the space of all Diophantine equations, which ones are soluble over Z and which ones are not, right? So the first case where you encounter a failure to have solvability over Z is the case of degree 3, right? So Diophantine equation which degrees a smooth projected curve of degree 3, that is where you actually fail. So an elliptic curve is a sort of way out of this failure, because an elliptic curve is a smooth projective cubic, a degree 3 curve over some field. So for us, we will only take the field to be the rational numbers. It has a genus 1, and it has at least one rational point, right? So this is the way out. So these are Diophantine equations for which there's at least one rational solution that you know of. Okay, so when you do Diophantine analysis over Q, you can say that every elliptic curve over the rationals has a long Weierstrass form, which is given by this particular equation, y1 squared plus a1y plus a, oh, it should be an a1xy, sorry, there's a small typo here, xy plus a3y equals x cubed plus a2x squared plus a4x plus a5, where all the ai's are rational numbers. It also has a short Weierstrass form, which is this y squared equals x cubed plus ax plus b, where again a and b are rational numbers. And you can sort of go between these two. You can go, if you have a long form of the Weierstrass equation, you can always recover the short form of the Weierstrass equation. So for today's talk, we'll mostly be dealing with the short form of the Weierstrass equation. So on one side, when you think of an elliptic curve over Q, I want you to think of a Diophantine equation, which is basically y squared equals x cubed plus ax plus b, where a and b are rational numbers. Okay. So this is the simplest one. This is going to be the simplest form that we will encounter. So an elliptic curve also has many other renditions. You can think of it from the point of view of intersection theory, from the point of view of algebraic geometry, from the point of view of arithmetic geometry, and even in string theory. So for example, if you want to do intersection theory, an elliptic curve is just the intersection of two quadratic surfaces in three-dimensional projective space. And there's a very, very nice algorithmic way in which you can go from this quadratic surface intersection in three-dimensional projective space all the way down to an elliptic curve in P2, which is the one we just showed before. But a more familiar version to many of you in the audience is going to be the one that we're familiar with, which is the elliptic curve is basically the quotient of the complex plane by a doubly periodic lattice. Okay, so here var pi1 and var pi2 are the periods of the lattice, and then you can define a complex number tau as var pi1 over var pi2, which is valued in the upper half plane, and such that when you quotient out the complex plane by this lattice, you can apply something called the uniformization map, which is often sort of pushed under the rug, but then that gives you an elliptic curve, which is a torus. Okay, so in some sense, you can also think of a connection between the equation that I showed here before, which is that if I have a particular elliptic curve of this form over here, then this equation, you can compute the periods of this equation, and they're going to be exactly W1 and W2 over here. Okay, but you can also ask of them in terms of something more interesting, which is what happens if you want to plot them. Okay, so if you want to plot elliptic curves, well, they look something like this. So I'll plot the exact same curve that we saw earlier. So elliptic curve y squared equals x times x minus 1 times x minus k squared, and it has a discriminant given by this expression over here. So let's recall that the discriminant basically tells you whether or not your elliptic curve has repeating roots or not, meaning that in this case, if this is a non-zero expression, it means that the roots are not the same. If the expression is 0, then it means the elliptic curve has repeating solutions. So let's try to plot this and see how this actually works. So I'm going to quickly show you a small video. Let me get out of here. Oops. So this is what happens when you plot the elliptic curve and you vary the curve. So basically what you see is that as this is happening, the discriminant changes. At some point it goes to 0 and eventually comes back to -1 and then goes back to 0 again. So you will see that the curve sort of changes. It goes between something with these two connected components to something with one connected component and back again. Right? So this is what elliptic curves over R actually look like. Okay, so the key important part here is that we want to understand rational points over elliptic curves because that's where the very, very nice story is. So we know that elliptic curves have at least one rational solution, which is given at the point, which is traditionally called the point at infinity. And if you want to find rational solutions over elliptic curves, you can sort of use a very nice approach, which is known as Bézout's theorem. So Bézout's theorem basically tells you the following. So let's say you have a degree P equation and a degree Q equation, and you want to ask, well, you want to say, well, degree P and degree Q, they intersect each other. So these are two equations which have intersection points. And the Bézout's theorem tells you that the intersection, the number of intersection points, has to be at most degree of P times degree of Q, which is basically P times Q. So for example, if you have a circle, which is a degree 2 equation, and a straight line, which is a degree 1 equation, well, a straight line can intersect a circle at most at degree 2 times degree 1, at most at 2 points, which is basically what happens, right? When you draw a line through a circle, it's going to intersect the circle twice. So here you have a degree 3 curve, and you have a degree 1 line. And what you want to do is that the name of the game is basically that if you have a rational point P, if you draw a line with a rational slope through that point P, any rational slope through the point P, such that it hits another rational point Q, then it's guaranteed to hit a rational point R. So it's sort of a bit weird why I've drawn this here. Why is it that I've drawn P plus Q and the point R is reflected down here? But actually, it has to do with respecting this particular equation. And for reasons of something called group law of the elliptic curve, we actually use reflection. But let me already tell you what the group law of the curve actually is, meaning that if you take 3 rational points on a line up to this reflection, then they're always going to lie on the straight line, right? So you can have, for example, over here, P plus a double tangent C at Q. So you get P plus Q and Q, and this is going to lie on a straight line. So that is basically what this 0 means over here. So if you have P and Q, and the other point being the point at infinity, then you make note that they all lie on a straight line. And then you have P plus Q. Oh, this should have been repeated. It should have been basically tangent at P only. So then it should have been a double tangency point at P alone. So it'd be P plus P equals 0. So the figure has been incorrectly rendered in LaTeX. I apologize for that. So basically, to respect this group law over here, you need to have this double tangent, this tangency law, this rationality of the slope basically having reflection. So when R goes to minus R, you'll have P plus Q, then the R, which is now reflected, will give you 0, basically. So this is how we think of the curves. But another way to think of this is that if you have a solution, so P is going to be a pair X comma Y, Q is going to be another pair X comma Y, then if you actually add these solutions up, then basically you can substitute them with the equation of the curve, and you will find that the form of the curve does not really change. So that's another way to think about what the solution, what the addition of solutions actually means. Right. So the set of all solutions of an elliptic curve is denoted EQ, and it's famously an abelian group, right? Meaning that you can add solutions on the point infinity, and you use the Bezout theorem approach, and you actually will generate new solutions to the curve. So this group is famously known as the Model-Way group of the elliptic curve. It was famously conjectured by Poincaré that this group EQ is an abelian group. And I think about 20 years later, his student Mordell proved that it indeed was an elliptic curve. Okay, so let me quickly summarize what we've done here so far. We have treated elliptic curves, which are cubic equations, which arise as sort of arise in the arc length, which arise as sort of differential equations satisfied by the integrand of an arc length formula. And we treated it from a point of view of Diophantine analysis. You can treat of it from a point of view of arithmetic geometry. You can look at it from different points of view. But when you look at it from the point of view of Diophantine analysis, this particular equation admits rational solutions. And the way to generate these rational solutions is basically to use this method of rational slopes and Bezout's theorem. But then you find that the set of all rational solutions was proven to be an abelian group. So that's where we are right now. And the number of rational solutions is basically what we're going to be after at this point in time. So before we go into the number of rational solutions of an elliptic curve, let me take a quick sidestep into another very important theory, which is known as complex multiplication. So unlike the name suggests, it's not simply the multiplication of complex numbers. And in fact, David Hilbert calls complex multiplication in one of his writings that it is the most beautiful theory in mathematics, but not only the most beautiful theory in mathematics, but also all of science, right? So roughly speaking, complex multiplication is the study of the beautiful, beautiful structures that arise in the interplay between any algebraic variety when the endomorphism algebras are defined over imaginary quadratic fields. So I know that's a lot of words to process right now, but let me tell you what it actually is, okay? So EQ is complex multiplication if its endomorphism algebra is larger than Q. So let's take a step to digest what this actually means, okay? So an endomorphism algebra is basically something that preserves the group structure. So we know that the group of solutions has a particular group structure, meaning that you can add these solutions and get another solution with respect to 0 element, and then you can generate all the rational solutions on the elliptic curve. So usually these rational solutions more or less correspond, you can compute these endomorphisms basically by scaling the elliptic curve up and down. So just simple scaling of them, think of them as think of them as just multiplying the lattice, which defines the elliptic curve. You can just multiply its size by some arbitrary integer, and you will see that this still respects the endomorphism of the elliptic curve. But every now and then, what you could see is that the lattice can actually be rotated, right? Meaning that it's no longer just a simple blow up, simple shrinking or rescaling by an integer, but actually there's some action of an imaginary number on the lattice, which leads to rotation. So this basically, when this happens, such that such transformations preserve the endomorphism structure of the elliptic curve, then you say that the elliptic curve has complex multiplication. It actually also has very, very close ties to Galois theory of elliptic curves. It has very close ties to theta functions of elliptic curve, which I'll tell you about a bit later. But for the point being, we want to do something very, very algorithmic, which is that we want to understand, we don't want to think about endomorphism algebras, we want to think about something that we can compute in our heads, okay? So an equivalent definition is to say that the elliptic curve is complex multiplication if its J invariant is an algebraic integer, right? So let us recall what the J invariant actually is. So the J invariant is basically given by this very famous J of tau, where tau is now the modulus or the complex structure of the elliptic curve, which is the periods, the var pi 1 over the var pi 2. So if you take the J function, you evaluate that guy, you'll get the J invariant of the elliptic curve, okay? And this is basically 1728 times G2 of lambda cubed divided by G2 of lambda cubed minus 27 G3 of lambda square. This is very standard stuff. I'm pretty sure it's also there in many books on string theory. G2 and G3 are the functions that appear in the Taylor expansion of something known as the Weierstrass P function. And these are the Weierstrass P functions generates for you the field of all odd elliptic functions. So this is almost canonized in complex analysis at this point, so I'm not going to go too much into this. But if you want to take, for example, a curve, so the curve, let's say y squared equals x cubed plus x, this is a cubic curve. But if you have the transformation y tends to iy, x tends to minus x, well, this preserves the structure of the curve, but this is no longer a scaling by an integer. It's scaling by a complex number. So therefore, this curve actually has complex multiplication. And you can ask a very simple question now. Okay, the audience is mostly full of string theorists and physicists. Why would someone care about this? Well, I won't go too much into the physics part of it in this talk, but complex multiplication is a necessary condition in the rationality of superconformal field theories and even conformal field theories for abelian varieties. And it's been known for a very long time. For example, if you take a conformal field theory whose target space is an elliptic curve, then it's been known for a while. Actually, Greg Moore showed it, and also Katrin Wendland showed in her PhD thesis that complex multiplication of the elliptic curve is required. It's basically what tells you about rationality of the superconformal field theory or the conformal field theory. Yeah, and so for example, we also saw them arise in Sergei's talk yesterday, the M-theory compactification, but they also appear in attractor mechanisms, which we saw today morning in Abhishek's talk as well, and also in Sergei's talk. So the famous conjectures on the attractor black holes are that if you take an n equals 4 attractor, for example, which is done by K3 times elliptic curve compactification, then it is necessary that the K3 is singular and the elliptic curve is complex multiplication. Singular here means that the Picard rank of the K3 surface is going to be 20. Okay, so there's no free moduli, so the transcendent lattice has rank 0, so the K3 has no, I mean, in that sense, it's singular. Okay, so, and the elliptic curve is complex multiplication, but also you could do it for the case of n equals 8 attractors. So this is a T6 compactification where you can think of as E times E times E, and each E is now a complex multiplication elliptic curve. So these are the famous conjectures that were conjectured by Greg Moore back in his famous paper on arithmetic and attractors. And so fundamentally, one of the key ideas that I'm working on, but I won't present on right now, is to understand the relation between complex multiplication, arithmetic, and how the physics of these different objects actually talk to each other. Okay, so that is what complex multiplication roughly is. So it's...
Sorry, Abhiram, is this conjecture for n equal 2?
For n equals 2, that's a very good question. So for n equals 2, it's a bit more complicated. It's a bit more recent. This is what Philip lectured about in Trieste as well. So for the n equals 2 case, you have to look at whether or not so first of all, Calabi-Yau, when you go to Calabi-Yau variety, so for abelian varieties, complex multiplication is first of all very well defined. But when you go to an algebraic variety like a Calabi-Yau manifold, the notion of what it means to be complex multiplication is not so well defined. So you have to think about it in terms of either splitting of Hod structures or, for example, something called factoring through of Galois representations. But if you think of it at the time of splitting of Hod structures, meaning that the middle cohomology of the Calabi-Yau manifold has a particular interesting split, then you will actually see attractor points. So the statement for the n equals 2 case would basically be that you should see persistent factorizations of the zeta functions of the Calabi-Yau manifold. So, for example, if you look at the paper by Elmi, van Straten, Candelas, and De La Osa, then they find a particular example of an attractor point in the so-called Hulik-Werl family, where they show that there's one particular point in this family. It's a parameterized, it's a one parameter family, and there's one particular point where you see that the zeta function has very constant factorizations. And when you look at this is what Gabriel and I also saw in our little side project, is that when you actually go to this particular point in the attractor chamber, then you will actually see that this actually does solve the attractor equations. So for the Calabi-Yau case, I think it's slightly more involved, but I think the reason it's a bit more involved is because there are we don't know what the correct definition of complex multiplication should be for the case. But if the takeaway from this actually is anything, it's that for the n equals 2 Calabi-Yau cases, the condition for our attractor should basically be that there should be persistent factorization of the zeta function of the Calabi-Yau, meaning that the polynomial, I will show you a bit later, there are polynomials which appear in the zeta functions. They just have to factorize the smaller and smaller pieces. So that would be the case. It's probably better to show this with an example. I don't have an example prepared right now, but I will send you an example by email, if that's okay.
For K3, the complex multiplication is well understood?
That's a very good question. So for the K3 cases, it's sort of known. Well, K3 first of all is also algebraic, but it's known in certain cases, for example, the so-called Shira-Inoue cases, that if you have an elliptic curve, if you think of K3 as elliptic curve times elliptic curve, such that the two elliptic curves are CM, then you can say something about the K3 complex multiplication as well. But also from the K3 as well, it's better understood through Hodge theory. So this is quite well explained in Claire Voisin's book on Hodge theory and complex surfaces, or complex manifold, complex geometry, I think. So the two-part book. So I think the moment you go beyond abelian varieties, you have to start thinking about it from the Hodge theoretic point of view. And whatever that means, I'll tell that to you in an email later on, because I think that will sort of divert us from the main point of the talk. Is that fine?
Yeah, thanks.
Okay. But that's a very, very good question. Okay, so now let me talk a little bit about classification. So far we've studied, sorry, just take a quick water break. So let me also, so far we've studied, I've talked about elliptic curves, but complex multiplication of elliptic curves, that it's this thing where you have endomorphism, enlarged endomorphism of elliptic curves. But essentially what you want to think about is that the J invariant, you take the J function, you take the tau of the elliptic curve, plug in that tau. So this is the same J function, E4 cubed divided by eta to the 24. Take the tau, plug that in there, and you see if the value is an algebraic integer, then the curve that corresponds to that particular tau has complex multiplication. That's all you need to remember. So if you want to study more about complex multiplication, this particular paper that I wrote with Masaki Okada and Taizan Motari has a huge, very large pedagogical section aimed towards string theorists. So yeah, you can go have a look at that. But for time being, what we've now done is that we've studied rational solutions, how to characterize them, and theory of complex multiplication. And we want to start putting these things together. So the first ingredient we need to put these things together is to classify elliptic curves. So there's a very famous theorem which tells you that elliptic curves over C and over R are completely classified. So over C, I mean S1 times S1, like Sergey, you mentioned yesterday in your M-theory compactification, which is over C, every elliptic curves is simply S1 times S1. Over R, it tells you, you can classify them depending on the number of connected components of the curve. So remember in the original picture that I showed you, or in the thing that I showed you, you had a curve which basically broke off and then came to one piece and then went out into two pieces again. So that is the number of connected components of the curve. So basically, the curve is completely classified depending on how many connected components it actually has. So if it has two connected components, it's basically just a Z2, which comes from this piece. I don't have the figure here. Okay, it's two connected if the discriminant is less than 0, and S1 if it's one, and it's S1 if it's greater than 0, that it's one connected. So the discriminant of the curve is basically for a curve of the form y squared equals x cubed plus ax plus b. The discriminant is basically defined as minus 16 times 4a cubed plus 27b squared. Right? So this is just going to be a number that you get out. Actually, an integer or a rational number that you get out. Okay, but if you want to classify the curves over Q, this is actually much, much harder to do, right? Because Mordell showed in the 1920s that the elliptic curve group EQ is actually an abelian group. And there's a very, very famous theorem called the fundamental theorem of abelian groups, which tells you that every abelian group decomposes into a finite part and an infinite part, right? So if you want to think about this from the point of view of elliptic curves, there's something called a torsion part. So this is basically a set of curves. Think of the elliptic curve that I just drew, and think of all the different points of the elliptic curve. So basically, the torsion part basically tells you that if you start off with one particular rational solution, draw a line to one other rational solution, such that you discover a third rational solution and repeat a different sort of process to find other solutions, then eventually you will hit a cycle and you'll come down. You'll basically form a finite set. So you'll form a finite cycle, so to say, in trying to find the rational points. That's what the torsion part of the group is. But the rank part of the group basically tells you the number of inequivalent families, meaning that you can apply this theorem over and over and over again, and you will never converge back to the original point again. But it just tells you the number of such different families on the curve that there are, such that you basically have an infinite number of points on this particular family. So the number of inequivalent families tells you about the rank of the particular curve, right? So it decomposes into a finite part called the torsion part, and it decomposes into an infinite part called the rank part of the elliptic curve. So in 1978, Barry Mazur proved that the torsion part of every elliptic curve has to fall into one of these two categories. So it's basically in Z over NZ for N in, well, it should be, there's no 1 here. So 2, 3, 4, 5, 6, 7, 8, 9, 10, and 12. And it's Z2 times 2NZ, where N is now in 1, 2, 3, 4. Let's copy the one up here. It's the mistake is a small typo here as well. So, and the rank of the curve actually is also a computable thing. So if you work really, really hard, there actually are ways through something called Galois descent in which you can compute the rank of the curve, but there's absolutely nothing known about the rank of the curve, right? There are, of course, very nice experimental results that start off with the original work of Birch and Swinnerton and Dyer, and also with more recent work, thanks to our friends Yang He, Q-Han Lee, Tom Oliver, and Alexei Potsnikov, where you can sort of see some sort of structure in the classification of the rank of the curve, but there's really nothing to tell you that there's an upper bound on the curve, that there is no classification of the ranks, there's no distribution of the ranks, there's no prediction of the ranks. So there are certain results assuming, the generalized Riemann hypothesis. There are only a finite number of okay, maybe I don't want to go into this at this point, but there are certain heuristics on the number of ranks with, arbitrary, a number of curves with arbitrary large rank as well. So that's a paper by John White and a few others. So yeah, there are also, but at some point we don't know what, we have a very few, we don't understand these 4 questions very, very well. Okay, actually very minimally, I would say. So one of the first things that people started studying towards the rank of the curve was that the famous Burton-Swinnerton experiment. And many of us were lucky to visit this particular building to see the original computer that they used, and also to see the documentary about their fantastic, joy-filled, love-filled lives in Cambridge. But so Birch and Swinnerton basically started studying point counts of elliptic curves with known ranks. And they observed a lot of different patterns. Particularly what they observed was that when you take an elliptic curve over FP, what that means is that you take this particular equation of the curve and you ask for solutions X and Y over the finite field FP, where finite field goes from 0 all the way to P minus 1, right? So you're only searching over a finite set. And the number of solutions that satisfy the elliptic curve equation is referred to as number of elliptic curves over FP. And I found this particular relation. With more and more data, they actually computationally generated a very, very important conjecture. And this important conjecture is one of the most amazing conjectures, I would say, in number theory and arithmetic geometry, because it relates the algebra, the cohomology, and the arithmetic and elliptic curve to an equally very, very mysterious object known as the Tate-Schaffer-Rayvich group. That's a very, very difficult conjecture to understand. But very roughly speaking, the conjecture tells about something known as the L function of the elliptic curve, which we will come to in just a bit. But it tells you that there is this function attached to an elliptic curve called the L function, and it's a meromorphic function, and the order of vanishing of this function at s equals 1 is equal to this rank, which is really, really bizarre because the rank is something that you compute through algebraic means, but the L function, as I will show you later, is something that you compute through very arithmetic means. So what this conjecture at its very, very core is telling you that the algebra of your curve comes from the arithmetic of the curve and vice versa. Okay, and this is why it's such a beautiful problem, and this is why it's part of the unsolved Millennium Prize problem as well. And very, very interestingly, this is also one of the problems that we expect to generalize under the Langlands program, which is that if you were to go for Calabi-Yau varieties or Calabi-Yau motifs, there are analogous statements of the BSD conjecture. And the conjecture, for example, for Calabi-Yau variety, it's it's very close related cousins of the Deligny conjecture or the block conjecture and so on. So this is a very, very important conjecture that has very important general applications also beyond the space, beyond the study of elliptic curves. But this is one of the first cases where you use experimental methods, computational methods, computer methods to actually start studying things about elliptic curves. So that will be something that will come about quite a bit in the rest of the talk, which is using computational techniques to study elliptic curves. So I mentioned this word L function over here. I didn't really motivate it. I apologize for that. I'm going to do that right now. So to do that, we want to start off with studying something called the zeta function of an elliptic of any variety x over q. So you take a smooth projective variety. So it's a projective variety, meaning it's a polynomial in projective space. It's smooth, meaning it's not a singular, it doesn't have singularities. It's over q, meaning that if you write it as an equation, it has coefficients in q. And you want to count the number of points over the finite fields, fp, which basically is 0 all the way to p minus 1, or more generally, fp to the n, right, which is called the Frobenius action, but we don't need to know this right now, where fp of n is defined as this particular, way. And there are three functions that you can attach to any such variety. So there's so-called local functions, and there's something called global functions. The local functions need prime as an input, whereas the global functions don't require the prime as an input, right? So it basically, the local zeta function is just another typo, should be a bracket closed over here. So the local zeta function is just a generating function for the number of point counts. So we call this the point counts. It's a generating function for the number of point counts of a given variety over the finite fields, all right? And it has this particular form over here, whereas the global L function is defined as basically taking the product over all the primes of this function, and you're setting t equals p to the minus s for some sufficiently large s so that it converges. And it's very important to remember that the degree of the polynomial p is b of I if the variety is smooth, and when you reduce it mod p. So, and from this you can construct another function of the Hasse-Weil zeta function, which is just basically the product over all the primes of this Li of x, which in some ways basically product over all primes, the zeta function of xp, which t equals p to the minus s. So this is a bit terse, but let me try to give you an example. So for example, if I take x as a point.
Sorry, Abhiram, can you return? Well, the first function is defined in a kind of plethistic way, yeah?
Sorry, what way?
Plethistic, I forgot what's the right
okay.
spelling. Just you have exponential and then you have sum of powers of n divided by n, yeah?
Mm-hmm.
Why is that? I mean, why not just simple generating function?
You mean why not just like write a modular form or some Q series or something?
Yeah, why not just sum and
so it turns out that if you write it this way, why do you want to define a zeta function this way? Let me give you an answer. So firstly, to answer the second question, the generating function that you expect sort of falls out if you define zeta function like this. But I'm trying to remember my Rosen and Ireland textbook right now. I'm not trying to understand. I forget the motivation for why you define the zeta function this way. I apologize, I don't have an answer for you right now, but I'll answer the second part of the question, which is that if you define a zeta function this way, then your generating function, like the one you want in modular forms or Q series, that drops out. And I will show you this as well. Okay, it's probably not a satisfactory answer, but I don't have a better one for you at this point in time.
Yeah, I'm wondering whether this plethistic nature is used somehow.
We'll see. Okay, if by the end of the talk I haven't answered your question, ask me again. Okay, so because I want to show you this one particular thing, which just falls out like magic in some sense. Okay, are there any other questions? I want to show you one example. So for example, if I take x to be a point, then the Hasse-Weil zeta function is simply the Riemann zeta function. Okay, so it's easy to work forward because then you can show that most of the polynomials are sort of trivial. And I could show you how this, if you might not be able to see it from here directly, but I can show you why if you take x as a point, then the Hasse zeta function is simply the Riemann zeta function. So in some sense, all the L functions that you think about, like Dirichlet L functions, they can all arise from geometry. So if you take Dirichlet L functions, they would arise from something called schemes, not as points. But we are interested not in terms of points and schemes, we're interested in curves today, okay? So attached to these zeta functions are some very, very influential conjectures, which were conjectured by André Weil back in the 1950s, called the Weil conjectures. So the Weil conjecture tells you that the polynomial pi of x where q is some p to the something, is a rational polynomial of t of degree bi of x. Bi is the ith Betti number of x, assuming that when you reduce the curve mod q, it still has good reduction, meaning that it doesn't become singular or the discriminant doesn't become zero. Okay. So secondly, the conjecture is that the functional equation has has a functional equation, meaning that you can sort of continue it to the entire complex plane using this particular relation over here, where n is basically well, what the n actually is, it's a very interesting thing. It's related to something very deep and motivic. I don't want to get into that right now, but chi of x is the Euler characteristic of x, and zeta is basically the zeta function that we defined earlier. And thirdly, the roots of all the pk have real part k equals 2, right? So these were a very influential set of conjectures, and basically they have all been proven, but they're still called the Weil conjectures because of very historical reasons. The rationality of the P of I was proven in the 1950s by Bernard Dwork. The functional equation of the form, to show that the functional equation has a particular form and it exists, was proven by Alexander Grothendieck, one of the most influential algebraic geometers of the last century. And the last part of this, that the roots of all pk have real part k as 2, was proven by his student, or maybe not student, Pierre Deligne. So the last two equations, the derivation of the functional equation and proving that the roots of pk, they both have been, these are both Fields medal winning works, and because of the kind of technology that they actually came up with. So for example, Grothendieck found that a particular way of attack that he could think about this problem was through developing a theory of something called motives. And then eventually, when that didn't work, he abandoned the theory of motives, and simultaneously, Deligne developed the theory of so-called étale cohomology, and he proved a lot of interesting results, in particular proving the Ramanujan conjecture. Ramanujan conjecture, of course, many of you know, is that if you take eta to the 24, then it tells you, and you Fourier expand this, then every primed Fourier coefficient is basically bounded from above in absolute values by p to the 11 halves. So this is the Ramanujan conjecture, and that proof actually goes into this particular proof over here, right? And this also appears in other branches of physics too, because the zeta functions and so-called understanding the relation with arithmetic geometry and algebra is something that also appears in different structures of physics. It also appears, for example, in Feynman integrals. Thanks to work with people like Francis Brown, Spencer Bloch, Matt Kerr, et al., that these are things that also appear in precise computation of Feynman integrals. Okay, so what we want to do now is basically try to relate this to the rational point story, right? So let's take a particular curve, y squared equals x cubed plus ax plus b. So I've taken the curve over here, y squared equals x cubed minus 12x plus 7. And if I reduce it modulo 13, I get something that looks like this. I get a collection of points that looks like this. So what I'm interested in counting is the number of solutions modulo a given prime, okay? And that is something that can be encoded in the zeta function. So for example, for elliptic curves, if you work through the procedure that I wrote down earlier, you follow write down the polynomials, the Betti numbers of the elliptic curves, and then it tells you that the zeta function of the elliptic curve is basically given locally by this particular form over here. Okay, and AP here is a very, very important thing because AP is related closely to the number of point counts of the elliptic curve. So there's a very, very beautiful theorem by Hasse and Weil that tells you that for all primes P, the number of solutions of the elliptic curve reduced modulo P is basically P plus 1 minus this AP over here, right? Where AP is bounded in absolute values by 2 square root of P, right? And So, for example, you might ask where this one comes from. Well, this is just a mark point in infinity. This is a very beautiful bound that one can derive, but this too is called the Hasebe bound. And this will actually play some role, maybe not today, but I've mentioned this in different talks. I also mentioned in the talk in Montpellier that this bound actually tells you a lot about complex multiplication of the elliptic curve. So from this, you can define the elliptic curve L function. And the elliptic curve L function is just the product of all primes of something called as local Euler factors, and these local L functions. And these local L functions are basically defined like this. 1 minus APP is a minus S if the prime divides the discriminant of the elliptic curve, meaning that the curve becomes singular when you take modulo that prime, or it's divided as 1 minus APP is a minus S plus P to the 1 minus 2S when P does not divide the modulus, the discriminant of that elliptic curve. And this is a very, very famous conjecture that was made by Taniyama, Shimura, and then also by Andre Wei, but then eventually proven by Andrew Wiles, then refined by Wiles and Taylor, then finally proven by Breuil, Conrad, Diamond, and Taylor, that the generating function for all these APs, right, is a Hecke weight 2 eigenform on gamma 0 of n, where n is the conductor of the elliptic curve. I haven't really written down explicitly what the conductor is, but roughly speaking, the conductor is the product of all the prime factors of the elliptic curves. Okay, so it's some modular from on gamma 0 of n. So once you know the modular from gamma 0 of n, and if you can show that it actually belongs to the so-called new form, as new space, because it's a weight 2 Hecke eigenform, then you can check very easily from the coefficient, you can compute the number of points in the elliptic curve, and you can also basically compute the theta function of the elliptic curve just from a modular form. And this is the most powerful result, which actually is also one of the kickstarting points of the Langlands program, that you can relate on one side number theory of elliptic curves, and the other side you can relate harmonic analysis that comes from modular forms. Okay, I have 15 minutes more, right?
Right. Yes.
Maybe
yes,
less.
Yes.
Okay, I probably won't need all the 15 minutes, but I'll try to give you something, because this is where things start to get a bit easier. So another example where, so we're trying to switch the gear towards a little bit, and this is towards a program called Arithmetic Statistics of Elliptic Curves. So arithmetic statistics of elliptic curves is or of any algebraic variety basically is roughly to find any sort of statistical patterns relating the APs or the Ps, or to understand different sorts of objects attached to elliptic curves at different values of primes. So a very famous example that's been in recent use is the work of Yang-Hui He, Q-Huan Lee, Tom Oliver, and Alexei Potsdakov. I don't know if they are in the audience today. So what they did was a very interesting experiment, which is that they consider the set of all, so here I'm defining the conductor elliptic curve here. It's roughly the product of all the primes that divide the conductor, divide the discriminant of the elliptic curve. So if you consider a set of all, let's say you take the set of all elliptic curves of rank 0 and take the set of all elliptic curves of rank 1, and this is something that you know a priori, and you take those curves whose conductors lie in a particular range, say, for example, between n1 and n2, and you ask what the average values of APs are in that particular conductor range. Okay, so basically you want to ask the average value of AP is basically the average of some rank 0 or rank 1 is a number of elliptic curves between that particular, in that conductor range, divided times the sum over all the sum over all the APs of each elliptic curve in that particular set. Okay, and when you do this, you actually see a beautiful result, because as I told you earlier, predicting the ranks is very, very hard for elliptic curves. But what Yang-Hui He, Q-Huan Lee, Tom Oliver, and Alexei Potsdakov found was that you actually get this very beautiful result, meaning that you actually find this bias, or rather this almost mirroring bias between the average values of APs and the rank that is clearly distinguishes the rank of the elliptic curves. So this phenomenon has sort of been understood very well, sort of understood for elliptic curves right now, but there are lots of other things. And in fact, there's a lot more that I could say about this, but I do not unfortunately have time. But also it's expected that this also lies within a scope of the Langlands program, and that this is supposed to generalize basically to any so-called automorphic L function. Okay, and if you put them together, you get this beautiful picture, which Young, I think, decided to call it murmurations because it looks a lot like murmurations of starlings. Okay, and also as a shameless advertisement, I also want to point out that we're organizing a workshop starting in about 2 weeks' time at the Simon Center on murmurations precisely. But this question that I want to ask you differently right now, in maybe the last few minutes, is very, very different, which is that drop all these things. Take the set of all elliptic curves that you can think of, right? There's a huge, huge number of curves that you can look at. Okay, and they're, of course, they're all related by different relations, isogenies, isomorphisms. But if you take only curves up to isogenies, okay, you don't even need that at this point. Just take the set of all elliptic curves, and then using the modularity theorem, you know that to each elliptic curve, there is a corresponding weight to Hecke eigenform. Okay, so compute that weight to Hecke eigenform. Okay, and you ask the question, what happens if I evaluate the weight to Hecke eigenform at the complex structure of that particular elliptic curve? Meaning that you take an elliptic curve, you know its periods, you know its complex structure, therefore, meaning you know tau1, you know tau equals var pi 1 over var pi 2, and you know what the Hecke eigenform actually is. So take that Hecke eigenform and evaluate it at that particular tau, and what do you actually see? You actually see something very interesting. So when you have no complex multiplication, you actually see that there's a curve. Well, it looks sort of, because no non-CM curves are rather ubiquitous, you expect to see nothing much. They look like some dense collection of points. But when you go towards complex multiplication points, this is where something interesting starts to happen. They sort of look like the straight lines. And I should point out that the y-axis it doesn't really plot very well in Sage. The y-axis is the log of the square of the absolute value of the Hecke eigenform, and you evaluate this to like thousands and thousands of places over different conductors, and the x-axis is based the log of the conductor. Okay, so when you do this for complex multiplication, you actually see that rank 0 and rank 1 curves, they have the little shift. It doesn't really matter very much. But the reason why this happens, again, is due to a result in class field theory, which unfortunately I start to call CFT these days, is a result in class field theory, which tells you that these are all due to the behavior of the complex structure of the elliptic curve. And in fact, from these two diagrams, you actually can work out we worked out a very nice, interesting theorem, which you can implement computationally, which is that if I were to ask you, if I give you the elliptic curve and ask you, how do you determine the discriminant of the complex multiplication, meaning what is the discriminant of the field over which the elliptic curve has complex multiplication, then to determine that, you actually have this very nice thing, meaning that if I take the log of the absolute value of the elliptic curve divided by the square root of the minus the discriminant, then this answer is approximately equal to pi. Okay, and it's really not that hard once you get the basic proof. It can just tell you the world's Stark's proof of showing that square root of minus 163 is a unique factorization domain. To mathematicians in the audience, you will know exactly what I'm talking about. But very roughly speaking, this is a pretty straightforward, it's a very nice result. But what is very interesting here is the fact that the correction term depends on something known as the Deligne bound. So we saw this earlier in the talk by this morning, which is that we were interested in the growth of coefficients of different sort of automorphic forms. But for cusp forms, it's really not that straightforward to write down what this bound is. And it comes from something called Deligne bound. It comes from arithmetic geometry. And so for this particular Hecke eigencusp form, this is something that depends on the Deligne bound. It's a bit more complicated, so I haven't written it down here, but you can actually implement this very, very quickly. And in fact, if you're using a Pari version, which is less than 2.17, you actually can use our theorem to actually compute the discriminant of the elliptic curve very, very quickly. And in fact, so unfortunately for versions greater than 2.17, Pari just implemented a new command directly, but this is basically a very nice result. At this point, I want to quickly ask you I want to tell you what else is in the pipeline because I don't have much time. There are a lot more results on the arithmetic statistics of new forms of arbitrary weight. And we also have interesting results, which we can compare this to growth of coefficient of cusp forms from approximating pi. How well a cusp form approximates pi, you can compute the growth of Fourier coefficients of these cusp forms directly from this, and knowing the fact that they're complex multiplication curves or not. Or vice versa, if you know the bound, you can approximate pi. So at this point, you can ask, well, why should I care about these things? I mean, Abhiram, you're a string theorist. Why do you care about these things? Well, it's sort of very intriguing to see that starting from attractor conjectures, starting from rationality of conformal field theories, that there are these very, very deep arithmetic structures that arise in physics, especially in string theory and quantum field theory. So we've been seeing this in the precise evaluation of Feynman integrals. We've been seeing this in the attractor mechanism. We've been seeing this, for example, in rationality of conformal field theories. But the thing is, like, if you look at the picture a bit more carefully, just as I said earlier, just as in the case of BSD conjecture, you have something that's very, very arithmetic relating something that's very, very algebraic. Okay, so all these attractors, they have some relations. Attractor mechanism is a complex, the solution of attractor equation gives you a complex manifold. Why does a complex manifold care about the arithmetic of an elliptic curve? Right? That's a very interesting question to ask, nevertheless. At the same time, if you were to ask, well, the conformal field theory, the matrix of algebras, they're all a very algebraic setting. Why do they care about arithmetic of elliptic curves? So this is the program that that I've been slowly working towards. I don't really have much time to tell you about these things, unfortunately, right now, because I think I need more than 1 hour to tell you in each different setting what actually is going on. But I think this actually is a good point to stop with the concluding message, meaning that it's very, very important to take a step back and really see that there are these structures talking to each other right in front of our eyes. So they're truly worth investing some time into to understand them in all rigor, in mathematical rigor. So with that, I will actually stop, and thank you for your time.
Thanks very much, Abhiram, for this